computer. Okay, we are rolling. So, this is the MAE 318 controller design, and I am Jeremy Winter.
I'm Anastasia Dirkaluk.
My name's Jalen Franklin.
And I'm Nicholas Booth.
Perfect. Okay. So, I'm a junior majoring in aerospace engineering.
I'm a senior major in aerospace as well.
I'm also a junior, majoring in aerospace engineering.
And I am a junior majoring in aerospace engineering as well.
hmm
So first, we're going to go over the lab objectives and what the customer wanted the specifications to be. And we know that some of the specifications that he or she wanted, was controller should have a disk speed of 12 radians per second. It should have an over or undershoot that is hopefully less than 2%. One of the rise time to be larger than 1 seconds. Initial slope of the graph should be small, and the 2% settling time should be less than 0.2 seconds. The voltage of the controller that we're going to use here also is going to be a lot less than 24 volts.
hmm
Our controller design process started with testing the proportional derivative controller. Here on the presentation, you can see the graph that we had as an output. And you can see that the disk speed turned out to be not smooth, so there was too much noise in the data. Thus, we decided to test this setup with a low-pass filter. On this slide, you can see the output was a proportional derivative controller with a low-pass filter. You can see that the signal became much less noisy, but the average angular velocity of the motor was less than expected. Moreover, the state error was not eliminated completely because of the integral component. That's why we decided to test a different controller in the next experiment. We tested an integral controller. Here you can see the output of this controller, and the AI controller produces steady state error. Thus, the velocity of the motor was exactly matching the desired velocity of 12 radians per second. This time increased. That's why the box of the controller had to be changed in the CISO tool. So we set all the design requirements, and by changing the controller, we were able to satisfy all of them, and our final value of controller is 13.375 over S plus 25.
Before we went over which controller we chose, we wanted to have a list of pros and cons based off of the graphs that we were seeing in the previous slides. So first off, for the controller, one of the biggest pros was the steady state error decreased as the DC gain increased. However, the two pros that we have here, the cons outweighed it a lot. Being, not at a constant speed, it needed a larger voltage input to support that DC gain, and the high DC gains caused a lot of overshoot in the system. For the PI controller, the pros were it eliminated steady state error completely. It reduced the rise time, and the only cons were it just had a longer settling time and a narrower range of stability.
So, our final controller decision was based off those pros and cons and based off those plots of the angular velocity. We ended up choosing the PI controller as opposed to the PD controller. And the assumptions that were made with this experiment and our decision was that the disturbance in motor torque would be constant. And these assumptions allowed us to focus on the ability of each controller to match a desired angular velocity without having to consider other factors, external factors. And the PI controller was able to have the experimental output be the closest to the desired output, which was a big part in our decision. The trade-off, however, with this decision, as noted in the pros and cons, was that a big one was the PI controller was producing a slower response time. However, due to the pros of the PI controller and it being able to best fit the customer's specifications, it was the best decision for us.
So the controller we made was used to control the motor of an electric car. However, this can also be extended to other applications, such as medical devices within the medical industry themselves. Medical devices have a strict guidelines in terms of what they can and cannot do, um, mainly for the safety of the patients, and due to it also could potentially put their life in danger if it didn't work correctly. So a specific device that can control, like a defibrillator, it has a specific amount of voltage that it needs to administer to the patient, and it needs to do in a certain amount of time. So this controller can also be extended to that.
And that was a premature ending, but that's all, folks. Thanks for watching. Hopefully, you are happy with our decision, and thanks for watching.